Hi everyone. Today I'd like to talk about persistent memory plus RDMA, new age remote device. My name is Yang Xiao. I'm a software engineer at 1950s Nanda in China and have been working on Linux and related OSs for 6 years. I became a maintainer of Linux test project at the end of 2018. Currently, I'm focusing on persistent memory and RDMA. This is the agenda of my presentation. It includes 5 parts. I will explain why persistent memory with RDMA and show new specification of RDMA for remote PMEM. Then, I will share how to implement a new specification on soft RoCE and libIB verbs. And then I will introduce remote persistent memory access library. Finally, I will do a conclusion and share our future work. Okay, let me start from why persistent memory with RDMA. What is persistent memory? Persistent memory is a high-performance and byte-addressable memory device which resides on the memory bus. PMEM is the short form of persistent memory. It has many advantages. For example, data is not volatile after power interruption. It has nearly the same speed and latency of DRAM. It is cheaper than DRAM and provides a large capacity like SSD. User process can access PMEM in 4 modes: FS DUX, DV DUX, sector, and row. FS DUX and DV DUX are good for improving the performance because they are designed to access PMEM directly. Certainly, it's faster to access local PMEM in either FS DUX or DV DUX mode. However, modern IT systems and services need to transport data from or to remote PMEM, such as distributed database, distributed file system, key value store, and so on. Traditional TCP/IP became the performance bottleneck due to a lot of redundant overhead. Look at this figure. For example, copy data between user space and kernel space. Package data by the software TCP/IP stack of operation system. In this case, we need a faster access way to remote PMEM. RDMA is a good solution to access remote PMEM. RDMA is the short form of Remote Direct Memory Access. It is a technology that enables contributors in a network to exchange data in the main memory without involving operation system of either computer. It avoids redundant overhead because of its advantages. For example, provide zero copy between kernel space and user space. Bypass the host system's software TCP/IP stack, and move data without CPU involvement by DMA engine. Is it good enough to access remote PMEM by traditional RDMA? Not really. RDMA has 2 problems for accessing remote PMEM. The first problem is no guarantee of data persistency. Look at this figure. Responder returns acknowledge as soon as the RDMA write reaches the remote RNIC. The return data will be lost when it has not been saved into remote PMEM and the remote system is powered down. For data persistency, we need a way to confirm that the data is actually returned to remote PMEM. The second problem is no guarantee of data consistency. Two-phase commit is widely used by distributed database. For example, an application writes a blob of data by two-phase commit, like the following figure. Step 1, Write a blob of data into remote PMEM. Step 2. Mark the data as valued by updating an 8-byte value atomically. Another application can know if the data is valued by reading the 8-byte value. RDMA doesn't provide an API for atomic write yet as step 2, so we need a way to update an 8-byte value atomically. There are two ways to solve these problems. The first way is to introduce new specification to extend RDMA. It ends RDMA flush to guarantee data persistency, and ends RDMA atomic write to guarantee data consistency. The second way is to make a new up-layer library. It not only guarantees the persistency and the consistency of data, but also handles the complexity of RDMA and provides a set of simple API to applications. In addition, it will support a new specification in the future. Okay, I will talk about the above solutions and our effort next. Let me show new specification of RDMA for remote PMEM. There are two associations to make a new specification, IBTA and IETF. IBTA released the v1.5 specification in August 2021, and it defined the new RDMA operations for remote PMEM. IETF released a draft in March 2020, but didn't update it anymore. It also defined the new RDMA operations for remote PMEM. Intel has shared the overview of IBT's new specification on Storage Developer Conference. Today, I'll talk about IBT's new specification. IBT's new specification defines new RDMA flush operation. Look at this figure. A new RDMA flush can flush all previous writes or specific memory regions. It guarantees that the data is pushed to global visibility or persistency. It will send the RDMA read response with zero size to request after the data has been pushed. On both request and responder, the RDMA write and RDMA flush should be handled in order. IBT's new specification also defines new RDMA atomic write operations. Look at this figure. A new RDMA atomic write can write an aligned 8-byte value atomically. It will send the RDMA read response with zero size to request after the 8-byte value has been returned. On both request and responder, the RDMA flush and RDMA atomic write should also be handled in order. To support RDMA flush and RDMA atomic write operations, what must be extended in the stack of RDMA? As shown in the figure below, the whole stack of RDMA needs to be extended to support new operations. libIBWorks library provides RDMA API to applications, and it has not supported new operations yet. Currently, there is no hardware ANIC and related driver to support new operations. The next thing I'm going to talk about is how to implement a new specification on soft RoCE and libIBWorks. Why use soft RoCE? As I said, new specification requires hardware support usually. v1.5 specification has been released, but hardware vendors need time to make new ANIC. It may be a long time, and we don't want to wait the new ANIC. For this reason, we are focusing on soft RoCE driver, which is decided to make normal NIC support RDMA. Though it is slower than real ANIC, user can experience RDMA easily. Finally, we decided to extend soft RoCE and leave IB worse. This figure shows the software stack of RDMA based on soft RoCE. What is soft RoCE? We have to know RoCE v2 before introducing soft RoCE. RoCE v2 is the short form of IP routable RDMA over converged Ethernet. RoCE v2 is a network protocol that can transfer IB transport header and payload through the traditional Ethernet IP and UDP headers. If packets are formatted by RoCE v2, they can be forwarded by TCP/IP routers and switchers. Soft RoCE is software-based RoCE v2. It produces IB transport header and inserts it and the payload into the UDP header by software. The right figure shows the difference between hardware RoCE v2 and soft RoCE. Let me talk about how to implement a new RDMA flash process on soft RoCE. Please see the detailed logic of RDMA flash we implement. Step 1. When local soft RoCE processes a RDMA flash request from user space, it ensures all previous requests have been set by default, or ensures all previous requests have been completed by a fence flag. The fence flag is used to ensure the execution order of operations. Step 2. Local soft RoCE prepares a RDMA flash request packet by the following changes. And the new IBOP code RC RDMA flash OP code in base transport header. And the new flash extended transport header including selectivity level and placement tab. And specified the address and length to flash in RDMA extended transport header. Step 3. Local soft RoCE sends the RDMA flash request packet over UDP. Step 4. Remote soft RoCE accepts the RDMA flash request packet after executing all previous requests once. Step 5. Remote soft RoCE flashes the specified read and dips according to the content of flash extended transport header. Selectivity level defines the memory region regions the RDMA flash should apply on. Placement tab defines the memory placement guarantee of this RDMA flash. Step 6. Remote soft RoCE prepares a RDMA flash response packet by the following changes. Use IBOP code RC RDMA read response only OP code in base transport header. Set ARC or NUC in ARC extended transport header. Step 7. Remote soft RoCE sends the RDMA flash response packet over UDP. Step 8. Local soft RoCE accepts the RDMA flash response packet and generates the corresponding completion. Let me talk about how to implement a new RDMA atomic write process on soft RoCE. Please see the detailed logic of RDMA atomic write we implement. Step 1. When local soft RoCE processes a RDMA atomic write request from user space, it ensures all previous requests have been set by default, or ensures all previous requests have been completed by a fence flag. Step 2. Local soft RoCE prepares a RDMA atomic write request package by the following changes, and the new IBOP code RC RDMA atomic write OP code in base transport header. Specified the address and length to atomic write in RDMA extended transport header, and populate an aligned 8-byte payload. Step 3. Local soft RLC sends the RDMA atomic write request packet over UDP. Step 4. Remote soft RLC accepts RDMA atomic write request packet after executing all previous requests once. Step 5. Remote soft RLC writes the 8-byte payload atomically. Step 6. Remote soft RLC prepares a RDMA atomic write response packet by the following changes. Use IB opcode RC RDMA read response only opcode in base transport header. Set ARC or NUC in ARC extended transport header. Step 7. Remote soft RLC sends the RDMA atomic write response packet over UDP. Step 8. Local soft RLC accepts the RDMA atomic write response packet and generates the corresponding completion. Okay, let's go on to the next. How to implement a new RDMA flash API on libIB works. To support RDMA flash in IBV post send, we defined the new IBV WR-RDMA flash opcode to identify a flash operation, and added a new structural flash to transfer the information required by the flash operation. To support RDMA flash in IBV port CQ, we defined the new IBV WC RDMA flash opcode to identify a completed flash operation. The following code shows how applications use RDMA flash API. For example, post RDMA flash request by IBV post send. Get the completion of RDMA flash by IBV port CQ. How to implement a new RDMA atomic write API on libIB works. To support RDMA atomic write in IBV port send, we defined the new IBV WR RDMA atomic write opcode to identify atomic write operation, and take use of structural RDMA to transfer the information required by the atomic write operation. To support RDMA atomic write in IBV port CQ, we defined the new IBV WC RDMA atomic write opcode to identify a completed atomic write operation. The following code also shows how applications use RDMA atomic write API. For example, post RDMA atomic write request by IBV post send. Get the completion of RDMA atomic write by IBV port CQ. New RDMA operations are under development. Is there any available solutions? Remote persistent memory access library is an available solution. What is a remote persistent memory access library? It is a new library to access remote PMEM over RDMA. LibRPMA is the short form of Remote Persistent Memory Access Library. LibRPMA provides a complete set of API for applications to access remote PMEM, like RPMA send, RPMA receive, RPMA write, and so on. It has RPMA flash to flash previous write into remote PMEM. It also has RPMA atomic write to mark the previous write valued atomically after the previous RPMA flash had been completed. It will support new RDMA operations when they are available. Intel and Fujitsu are main contributors to libRPMA. Let's look at the basic API of libRPMA. I will explain the functions of some libRPMA API. For memory management, we can register memory region by RPMA rig and deregister memory region by RPMA DRIG. For connection management, we can create a new outgoing connection request by RPMA call req-new and obtain an incoming connection request by RPMA EP next call req. For messaging, we can send data to remote side by RPMA send and receive data from remote send by RPMA receive. For remote PMEM access, we can write data to remote PMEM by RPMA write, flush data into remote PMEM by RPMA flush, and write a 8-byte value to remote PMEM atomically by RPMA write atomic. In librpma community, there are 11 examples to show how to use various librpma API together. Let's look at the example 05 flash to persistent for details. Look at the following example. Client uses DRAM to register memory region by RPMA and RDMA. Server uses PMEM to register memory region by RPMA and RDMA. Client and server establish connection and transfer provide data by several RPMA core functions. With the connection, client can transfer data to remote PMEM by RPMA write and RPMA flush. Currently, flush and atomic write is not supported by RDMA, so how does librpma implement them? How to implement RPMA flush operation? librpma implemented RPMA flush by traditional RDMA read. Look at this figure. Requester sends a RDMA read as a RPMA flush. The RDMA read waits the completion of previous write automatically. The RDMA read flush or return data from RNIC to the remote PMEM before reading data from the remote PMEM. This way is called a appliance persistency method. How to implement RPMA atomic write operation? librpma implemented RPMA atomic write by traditional RDMA write with a lined 8-byte value. Look at this figure. Requester sends a RDMA write with a lined 8-byte value and a fence flag as a RPMA atomic write. The RDMA write waits the completion of previous flush by the fence flag and then writes the value. The RDMA write needs to be flushed to remote PMEM as well. Unfortunately, the RDMA write has to wait all previous read due to the fence flag. One more necessary consideration for RPMA flush operation. Inter-DDL is a key feature introduced on the Inter-Xeon E5 processor and Inter-Xeon E7 processor V2. As the Intel's document mentions, DDL makes the processor cache the primary destination and source of I/O data rather than main memory, helping to deliver increased bandwidth, lower latency, and reduced power consumption. With DDL, traditional RPMA flush using RDMA read can only flush data to the last level cache of CPU. So remote applications need to dream the data to PMEM by themselves. RPMA flush has to consider DDIO. How to implement RPMA flush operation with DDIO? In this case, librpma implemented RPMA flush by traditional RDMA send and RDMA receive. Look at this figure. Requester passes the address and read to flush to responder by a RDMA send. The RDMA send waits the completion of previous write automatically and then flush the return data from RNIC to the LLC. Responder flush or return data from LLC to PMEM according to the contents received. Responder notifies the requester the data has been returned into PMEM by another RDMA send. librpma is an up-layer library, so we would like to know how the performance of librpma is. How to evaluate the performance of librpma? librpma introduced the librpma dedicated engine to FIO so that we can use FIO to do the performance test on our environment. FIO is a benchmark to test the I/O performance. The table on the left shows common configuration of our environment. The example on the right shows the detailed steps to run the FIO benchmark on our environment. For example, client builds the latest FIO including librpma engine. It references sample jobs to create a new job file for the librpma client, and then run FIO with the client's job file. Server needs to do the similar steps as well. By FIO benchmark, we got the bandwidth and latency of remote PMEM access based on librpma and those of local PMEM access as shown in the tables below. Compared with local PMEM access, the performance of remote PMEM access is slightly worse. But I think librpma is still a good solution to access remote PMEM, and it may provide higher performance in the future. Okay, finally, I will do a conclusion and show our future work. In this presentation, I explained why PMEM with RDMA and showed the new specification of RDMA for remote PMEM. I also showed how to implement new RDMA operations on soft RoCE and libIBWorks, and introduced librpma. In the future, we will finish implementing new RDMA operations on soft RoCE and libIBWorks, and then push them into the kernel and RDMA core. We will also make librpma support new RDMA operations. Thank you for listening to my presentation. Please contact me by email if you have any question about this slide. Thanks a lot.